Right here it says the heater connection, left hand side very edge point. So that point it actually create the electron beam. Then you accelerate the electron beam and then bend electron beam according to the potential applied on this horizontal plate and the vertical plate, right? Only difference between cathode ray oscilloscope and the all type TVs, if you I don't know whether you guys ever seen the all type TVs. Like if you have a grandparents and then in the basement you might have a box kind TV, very big TVs, all type TVs. In 70s and 80s, even 90s, I think we had TVs like that. So those two TVs contain the cathode ray tube. Primary difference between the TV cathode ray tube and the oscilloscope cathode ray tube. Oscilloscope cathode ray tube, both of these horizontal and vertical plates work with the voltage, and the cathode ray which contain the all TV contain one of these plate is actually work with the magnetic field, not the electric field. So that's the primary difference. Other than that, both are actually the same. What both are doing is there's electron beam, you oscillate electron beam up direction, vertically on y-axis, horizontally and on x-axis, that you can observe right here on the screen. So that's all really. Very simple idea, but very useful. Still, we using this analog type oscilloscope to do certain experiment because digital one does not produce the results what we want to see. So that is still useful. But nowadays, most of the oscilloscope is actually changing to digital type. So the only difference analog to digital is digital oscilloscope does not contain this large tube. So that because this is a really large glass tube, inside is actually inactive air, some sort of argon, those kind of air is actually filled inside, right? So these are very difficult to work with. Usually larger. One thing is that, and the other thing is that it takes a lot of space. Now the digital ones, on the other hand, are simple, like your LED TVs. So LED TVs are very smaller compared to the TVs which we had 20 years ago. So that's the fundamental difference. And not only that, when you have a digital oscilloscope that can actually have more control than the analog. For example, analog oscilloscope have only 2 input, and the digital oscilloscope can have now even 4 or 8 input channels directly. So those are really good added advantage. And basic difference is that what the digital oscilloscope is actually does, it has analog to digital converter. Technically, you give the analog voltage, and then inside it has a circuit which convert all the analog signal into digital signal. Then you can see it easily as a digitized form. So that's the only difference. Other than that, the basic functionality is actually the same. Okay. And those things you can read as you working on the lab report. So the one other thing I would like to point it out here now, when you're doing your final project report, if you copy paste anything from outside source, for example, now this picture I actually took from this site, electronicsnotes.com. So that's not a reputed site which I would like to actually use as a citation. You should not do any citation like this one. I did not get a better picture like this one from the direct citation databases, okay? But in any case, if you use someone else's picture or someone else's information, you have to always give the credit. So you have to give picture credit to whatever the source you actually are using. Okay, so that's very important. Even in the lab report, I see sometime you copy paste from the pictures for your theory section for elsewhere, but you never actually cited that. Okay, either you have to write picture credit and then where's the source is, or you have to put the citation directly right here and then put it into the reference. Okay, both are correct. Make sense? Make sure your final project report should contain all of those. Good. and then basic ideas we discuss, and then beyond that you actually can read. Okay, this is a one good source you want to read more, and also you can go into these two sources right here. So these are directly, this is the way you should include the citation, right, references in your final project report. If you get anything from outside, Access Science will provide the APA style citation. Automatically, you can actually copy that whole citation from there and then put it into your references. Usually how you do the citation in most of the scientific journal, not the way you actually learn in your language and art classes. So that's something which we don't have any control. Usually, I don't know why we do that. In every college, people are trained to write the scientific report. Those teachers are actually language arts teachers. Some of those teachers never took any science classes in their life. Then they teaching a student to how to do the scientific report, that's something really laughable. Okay, but that we don't have any control. That's how the system works, right? So we don't need to worry about that. When it comes to scientific citation, APA style is also not working. MLA style also not working, right? If you take a look, what is the APA standard for, and then MLA stand for? Nothing is stand for science. But that is the one you learning in your first year classes, right? So that's something is really laughable. Okay, so you have to ask that question: why even we taking that class anyway? So that's the experience, right? You know how to write it down in APL, APA, and MLA format anyway. But when it come to the real scientific citation, we never put actually citation names there. Most of the journal, how they suggested to do in engineering and science, you put a number here. You see this one right here on this first column right here, paragraph, just after the picture. You see that number one, right? So that is how you put the citation. So I put that number one there, number two here, and then I include that numbers here in my reference list. Then I create in the reference list by putting the number one, number two, number three, number four, and then so on. That is the most general way of citation we do in scientific literature. So if you go into the language art literature, that completely different. They don't put the number there. They instead put directly the author's name, right? Patrick et al. And then put that citation details there. So we don't usually do that in scientific literature. And also in scientific literature, we never going to use inverted comma and then information from somewhere else. That we don't do. Because of that, on your final project report, don't put inverted comma and then write someone else's idea there. We don't usually do that. Okay, if you want to tell something you read from another page, another paper, you can rephrase that directly and then put a number to give the credit to that person. So unless if it is like a quotation, very specific, come from like Albert Einstein or somebody, then you can do that. Otherwise, we don't really do in scientific papers. Okay, so those are very fundamental differences from the language art, the literature papers and the science papers, but you can really learn those things. If you know one, you know how to write the literature papers on your language art classes. So now you have to just slightly tweak that to actually modify your the citation method, things like that, to align with the scientific journal. Okay, try to do that in your final project report. So that will be a good experience. Okay, any questions so far? All right. So, and also if you want to do the citation in very engineering format, you have to take a look IEEE format, right? So that's the standard engineering scientific format. You can just Google the IEEE citation format and then do that exact format on your final project report. That's another way actually you can get practice to what comes next, right? So when you go into the four-year college and then you start working real engineering classes there, then you will get the idea. Okay, so any other question so far? Everybody okay? All right, now what we're trying to do by using the oscilloscope today, we're not going to do really any serious experiment. Oscilloscope can use for many different important experiments, but we're not doing really anything very serious today. We're going to basically try to see by using the oscilloscope, we try to understand how to measure very basic information. So that's the plan for today's experiment. Let's take a look. Experiment number 8. Oscilloscope. So the oscilloscope has a screen, right? So that's the important thing. And there are a lot of adjustment screws. So since we're doing actually virtually, it is much easier. So this is a simulation we're using today. That simulation will give you very freedom of doing those adjustments. But if you're doing in class, oscilloscope has a screen, and then it has a lot of adjustment screws around it, right? This side it has a lot of adjustment, and then the other side it has a lot of adjustment, and then on below right here it has a lot of adjustment screws. And also it has usually 2 or 3 input channels. Analog type oscilloscope usually has input channels 1 or 2. Generally it says channel 1 and then channel 2. And if you take a look, this screen is actually, after you switch on, it has inside a vertical lines like that, and the horizontal lines like this. It technically like a graph paper, right? So these lines you can say like the centimeter lines in your graph sheet, and then in between the centimeter lines there's a smaller lines, right? So those are look like the millimeter lines. But in this screen, what you really read on y-axis, you reading the voltage, and then x-axis you reading the time. So that's what we read, right? This is in volt, this is in second. But when we reading this one, what you really read, why we need the oscilloscope, that's actually number one question. Why we need the oscilloscope to measure something? Anybody have any idea? So far in experiment, what you use is actually multimeter, right? So we use the voltmeters and ammeters. Those are generally called the multimeters, right? So the multimeters has actually all sort of facilities nowadays. If you take, there are 2 types of multimeters too, right? So the analog type multimeters, those are called the galvanometers, right? Remember the galvanometer? Galvanometer is actually, there's a scale, and then there's a pointer right here. Pointer can deflect, right? Those are very old type multimeters. For example, like 20, 30, 50 years ago, people had only those things. So those things can use to measure voltage directly, and also those things can use to measure current. And the galvanometers, you can't measure anything else. The multimeters in digital version can actually measure many. So the multimeters also has another version. So this is a galvanometer separately, and then multimeter itself has actually digital version and analog version. So the analog type multimeters has a scale like similar to this one. However, it can measure many different things in terms of, for example, voltage. It can have millivolt, microvolt, things like that. But still, it's contained this deflection, this needle, right? So that called the analog. And there's a digital version. In digital version, you have a scale, you can read the number directly. Those are the one we use in our lab setting. So the digital version has a more advantage. Those version has other measurement included. For example, you can measure capacitance directly, or you can test a diode by using those digital, and you can measure temperature, for example, directly by using those digital multimeters. So which mean digital multimeters has actually more advanced measurement can be done by using that multimeters. Usually current can be measured all the way down to microamps without any problem, or even less than that. So there are some digital multimeters you can measure down to all the way to a or the nanoamps level. nanoamps means 10 to the negative 9 level, very, very accurately. Okay, those are very expensive, but very useful in different experiment. Now, if you take a look the circuit, so yeah, the multimeters are good to measure all these measurement, and also these multimeters can measure AC and DC both, right? So you can measure by using multimeters AC and DC both voltage and current. But the galvanometers, particularly, it is not good to measure AC voltage at all, because if you put the AC voltage, this deflection needle gonna starting going positive and negative direction completely, and then it's not going to be any useful reading at all. So the DC measurement, yeah, that is good. But the multimeters can actually do all these measurement. Technically, you might feel that, okay, because of that, we don't need really oscilloscope to measure. Still, that is not true, because if you have a multimeter only, you can measure the values, those measured values, particularly for AC current. Now let's see what is the difference between AC and DC. If you have a DC current means value of that current which is actually fixed as a function of time. So as the time goes on, this current value never will change. Similar for the voltage, right? If you have a voltage measurement in DC, as a function of time goes on, you have the same voltage, like the battery, for example, right? VDC and then IDC. So like the battery, if you have a circuit, let's say I have a resistor circuit, and then switch and the battery, and then close the switch, then the battery will give you the current. So this current passing through this resistor is actually a constant value. You measure as a function of time, you read the same number. Similar for the voltage, right? You apply a voltmeter here serially, then you measure voltage across the resistor as a function of time, never change. It will give you directly this number, since there's no other connection involved. Now, if you have AC, what's the fundamental difference? Most of you know, AC current and AC voltage is actually fluctuate, right? So that's the fundamental difference. So you have a time axis here. If I have a voltage in unit volt, then the voltage and then current for the AC is actually sinusoidal function. So we will discuss this very soon in next few chapters. Now, if you take a look as a function of time, this value is starting from 0 and then reach maximum positive value right here. Let's say positive V0, and then decrease slowly and then reach other side, maximum negative value V0, and then decrease back, and then so on. It's going to continue forever as a function of time. Now, if you put this into a multimeter, you actually measure in what we call the RMS value. So that is called the root mean square value. That's the only number you can measure by using the multimeter. From multimeter, you can't really see this behavior at all. If you want to observe this whole behavior as a function of wave, then you need the oscilloscope. That's the fundamental need of oscilloscope. In very early time, like 100 years ago, when it discovered by using the analog type oscilloscope, by using the cathode ray tube. So at that time, what's the fundamental need is actually observing this whole waveform. But after that, nowadays, we are using oscilloscope, particularly in electronic engineering and then some mechanical engineering too. The oscilloscope is used to analyze various complicated circuits. Now, if I have oscilloscope, if you include the voltage, now for AC voltages, we're going to write this symbol right here. So circle and the curve like that. Just something like sine curve, something like S. So that represents the AC voltage, right? So if I apply a AC voltage to a circuit, this is the resistor, AC voltage, now let's say VAC. That will limit the current, but this polarity of the AC voltage is changing, right? You can see, if you consider AC voltage, always AC voltage has one important property, that has to have a frequency. So usually in our household outlets has a frequency about like 60 hertz, right? What that 60 hertz mean, frequency is actually 1 over time. time t is actually period of oscillation, right? So which mean positive and negative polarity of this AC voltage flip 60 times per second. So that's the idea. Because of that, if I just apply a multimeter across that, I'm not going to see that change. I'm going to see actually some constant value. That is actually what we call the RMS value. So what's the RMS value represent? We discuss this in detail later in the later chapters, okay? So the what RMS value is doing, if you have a function like this one, this function, I can't really say, if you try to measure something, I can't really measure anything because the numbers are fluctuating randomly all the time, right? This is positive and this is negative. If you add positive V0 and negative V0 together, you will get the 0. So what RMS value means, instead of that, let us square this, both of them, right? So let us square both of them. Then what you're going to see only positive value, right? Because the square of negative is also positive, right? So now first we'll square this. Now this is actually V square. Then let's take the square root of this. So if you take this square root of this one time and then V square root of that, that is actually called the VRMS. So you square first and all becomes positive. Then you take the square root is actually little bit lower now than the maximum possible value. Okay, that's the idea. Make sense? Following? First is square all of them, then add all of them together, and then get the square root of that. So that process at the end, what you're getting is actually called the RMS value. That is the only value we can directly measure. Make sense? Following? But if you have oscilloscope, what's the advantage? Oscilloscope is actually can give you this whole waveform. As a result of that, for example, I have a VAC supply to this R. I want to measure voltage exactly after some time, right here, after like 0.2 seconds. So you can measure exactly that voltage because this whole waveform is observable on your oscilloscope screen. So that kind of observation you can't do by just using the multimeter. So that's one of the important advantage. And also you can do other manipulation. If you add another resistor, another capacitor, for example, later when we talk about capacitor and then inductor, all of them together, LCR circuit, the digital ammeter or digital voltmeter or the multimeter itself doesn't useful at all. So we need to have the oscilloscope to see what's really happening inside them, particularly if we have the AC voltage applied. So those are the advantages and then usefulness of the oscilloscope for this kind of circuit analysis. Make sense? Any question? Which means generally you can say if I have a voltage supply AC type, multimeter itself doesn't provide all the information. Multimeter can provide some information, but to understand better, we need to have the oscilloscope measurements. Okay. Now let's take a look what oscilloscope is actually showing you. Now if you apply oscilloscope to your circuit, let's say I have a resistor here, R, and then I have a AC type voltage supply into my resistor, and now let's connect these two probes into oscilloscope, right? So this is actually positive and negative probes. Let's connect this into oscilloscope. Now usually if you have in-class labs for the oscilloscope has a probe. That probe has positive and negative end. Oscilloscope probes has a positive and negative end. But generally, that negative end, you don't need to connect to the circuit at all. So the probe contain positive end and negative ends, but only positive end should be connected because the oscilloscope internally has the automatic grounding. If you does not connect the negative end, doesn't matter. It will actually ground automatically for you. The grounding is actually done. Because of that, usually if it is in-class work, we usually connect only positive end. That is good enough to get the reading. And let's take a look what that screen showing you again. Now the y-axis, let's say this is a V voltage. Now I would like to measure that by using oscilloscope, right? Oscilloscope has various probes. Now if you connect this, what you're expecting to see is actually a wave. Sometimes you will not see the wave at all, or sometimes you will see wave is actually rapidly moving. Let's write it down, that part also here. Okay, so now we expecting to see that sine wave, right? So that's the idea. But when immediately after you connect this one, you won't see that at all, or maybe wave is continuously moving. Then the number one is that important thing is the trigger. So what trigger done by just slowly changing the trigger, you can actually stabilize the waveform on the screen. So in our virtual one, we have actually automatic trigger. And also the oscilloscope DC type has this automatic, it says auto trigger. So if you put it into the auto triggering, automatically what it does, it actually stabilizes the waveform. So something like this kind of waveform you can observe on the screen. Make sense? So that's very important. Before you do anything, always you have to put it into the automatic triggering. Okay, because if you don't do that, you will see this waveform is continuously moving on x-axis on one direction and the other. Because of that, you can't do measurement because it always moving, right? You have to stable first. That's one important thing always has to do. This is available in our simulation, and also this is available on digital version of the oscilloscope. Some of the updated analog version also has the auto triggering function, but very old analog oscilloscope doesn't have the auto triggering. Then you have to actually rotate a knob slowly until you stabilize this waveform. So that's gonna take a lot of time because there's a particular place it's gonna happen. You have to really find it out that by slowly changing the knob, triggering knob. After you trigger and then observe the waveform like this one, then the rest is very simple. Now y-axis tell you the voltage, x-axis tell you the time, right? Technically, let's say now earlier I mentioned you these things. So this contain like a square, right? A small square like that, many of them. And then x-axis also, you have a square like this, right? So now, for example, let's say these square values has on your channel, each channel has, let's say I have a channel 1 and channel 2. Channel 1 has a control, right? Channel 1 has a voltage control. Usually if it is a analog type oscilloscope, it's a knob. You rotate the knob and then around the knob it says certain values. What it says technically, voltage per division. So technically this division means one of this line right here, right? What it's telling you, this one large square is actually represent how much voltage, right? That's what it says per division. Similar for the time axis too, right? This is for the y-axis. And x-axis too, it is a knob. You rotating that, then the knob has some numbers written around it, and that says time per division. Time per division. That division means x-axis division, this one, how much time is that one. So which mean I can measure these two values. For example, I can measure from here to here. So if I know that division is, let's say in this case, there's a small lines in between this large line, you can read exactly up to here, right, this place. And then let's say that is 1.7 division, right? So each voltage value from here, you reading, let's say 1.2 volt per division in this time. Then all you have to do, voltage V0, which is equal 1.2 volt per division, then multiply by number of division from 0 to maximum point right here. That is 1.7 division, right? So division cancels out. You can find the total voltage, 1.2 times 1.7 in volt. Make sense? that you have to read carefully. Sometime, depending on this scale where it is, sometime it might say, for example, let's say another example, let's say this says this way, 1.2 millivolt per division. Multiply by 1.7 division, then the division cancels out. Your output come as a millivolt, right? Which means this part right here, which is very important, that coming from this controller, right? Now in your simulation too, you don't have a controller like this one, but you have actually to click something for that, and then you have to read that carefully. Okay, follow me? Make sense? Everybody okay with that? Which mean by knowing that I know the maximum voltage. And also if I do the same analysis for x-axis, what I can find. By do the same analysis on x-axis, for example, x-axis tells you I need, for example, the frequency of this one, right? Frequency is 1 over time. So this time is period of oscillation. Period of oscillation mean time for this is starting point. Whenever it completing one cycle, right, it has to go up, come back to the zero, and then go negative direction, come back to the zero. That is one complete oscillation. You find the total number of division, let's say 1 2 3 3.3 division, and then you find what is the value of x-axis. Let's say it says 1.5 millisecond per division, right? Then if I want to find the time, total time gonna be 1.5 millisecond per division multiplied by 3.3 division. Division cancels out, then you will get 1 over 1.5 times 3.3 millisecond. So then you take that number and then convert millisecond into second, that is 10 to the negative 3, that comes to the numerator, then you can find the frequency. If you know the frequency and the voltage, then you can explain given wave function properly. So that's the idea. To explain the wave function and everything, you need to have all those information. Make sense? Any questions so far? So that's why if you're doing this with the analog type oscilloscope, it's taking a lot of time. This measurement is very difficult to do sometime. But the digital oscilloscope has all of these, what we call the auto functions. So if you put the trigger into auto, channel 1, just click the auto, then you don't need to rotate any of these things to show it clearly. If you put the auto, it will show you the nice wave function without any problem. So if you have the digital, all these adjustment you have to do. So that's the bad thing with the virtual experiment. You will not get that experience by actually doing those things. Okay, any questions so far? Good, no problem. All right, then let's continue. So let's start the, I think everybody has a good idea what we're trying to do. So in today's experiment, basically what you try to do is actually you're going to measure these waves, right? So when it comes to these waves, there's a couple of different type of waves we're going to investigate. So we're going to set up a simple circuit, one resistor or two resistor with the voltage given. And then this voltage, usually what we interested is VAC type volt. Those are actually sinusoidal type waves, right? So those are this kind of waves. What we try to investigate is what's the maximum voltage V0 and what's the frequency. That means by measuring time for one complete oscillation, I can find the frequency. So those are the two measurements we try to do. And then later we can check if I have a clock type wave function. Clock type wave function is actually a digital type wave function. Instead of sine, I can give actually this kind of wave function. So sometimes we can give a triangular wave function, look like this, triangular wave function, and then measure that. That also has a maximum positive V0, negative V0, and also it has a frequency, right? So it completing one complete cycle, that called the period. So if you take the inverse, that will give you the period of oscillation. And also, I can give you switch on and switch off type wave function, which means wave function going to be look like this. So that's a digital wave function, right? So it has either switch on directly Now this part is switch on. You can see here there's no in between, right? It is 0, then switch on, and then stay there for a while, then switch off, then goes to the negative side, and then switch on, and then stay for a while, and then decrease to 0, right? So this is still the wave because positive and negative changes, polarity changes as a function of time, but this is a digital type wave function. So all of these you can analyze easily by using the oscilloscope. That's the goal actually. Very, very simple experiment, but it's time consuming. Okay, now any question? Anybody have any problems? All right, then let's start. Now, to do this experiment, what you need is a couple of things. So you need this virtual oscilloscope, right? The virtual oscilloscope, you have to really make a login for that one. You can click on this link, page number 4. It says multi-sim right here. Just click that link. That will open up a new window right here. Should be look like this. Okay, this is a very reputed company in America. So this is called the National Instrument. This whole simulator is actually produced by them. This is the company who actually own the LabVIEW. If you heard that, LabVIEW is very, very useful software which can actually communicate as an interfacing between hardware and software. So like similar to the concept you're doing with the other small free version of those communicating softwares, right? But this is a very, very advanced version. We're going to take a look very basics of this, but this can go all the way to a lot of advanced application. Okay. Now to go into this, you have to actually create a login. So you click a login and then create account right here and then fill it up that information what it asking. So if you create the account, it asking couple of information, your username, and you can put the name and then last name. Those are not really important. You can put just short version of that. Role right here, you can select a student. And email address, you can use either your school email or your personal email, doesn't matter which email you create, but make sure that email, you have to access that email to validate this account first, okay? So whatever the email you usually checking, so put that email. And then set up a password. And then after you put everything, click create account. And then after you do that, you will receive account to your email. And then you go into your email and then click the link, they send it to you. That will validate the account, okay? After it validate, then you can come here and then put your email and password, then you can log in. Okay, good. All right, try to finish that part first and then get it into this page. After you log in, it should be look like this, okay? This should work fine with any of the web browser. Shouldn't have any problem with any web browser. Okay, question. Anybody have any difficulty get it into that website? Okay, so you guys got the account done? Anybody get it into this page yet? Any problems? Okay, any questions so far? Everybody get it into this? Can we proceed to the next step? Or you need more time? Okay, good. Okay, so then all you have to do, your right hand side, very top, you will see create circuit, right? You just click on that. So after you click that, you will go into a new page that should be look like this. This is our simulator page for the oscilloscope. Okay, and this actually can be used to analyze very advanced circuit, not just the circuit what we're trying to do. We're trying to do very basic level circuit today, and this can be used to do very advanced circuit. You can see on your left hand side the selection tool. As you go downward, the first one is the voltage measurement, the sensors, right? Voltage, current, and then sensors. And then second one is the ground probe, and then the connector probe and the junction. And the next one you can see sources, right? Different type of sources. So we're gonna use basically this AC source only, but you can see there's many different sources, right? And right here you can see different type of items we can use: resistor, capacitor, inductor. Those are the three things we will be using this lab and the next two labs. But beyond that, you can use this with the different other circuit diagrams. So you can use a transformer, coupled inductor, and then so on. These are, you can create different circuit diagrams and then simulate. And then there are other lot of different selections you can do: diodes, LEDs, transistors, indicators, different switches, and then you can see different voltage supply here, and also electromechanical items, relays, and then so on, power, and then beyond that. Okay, these are actually digital gates, what we're telling. I don't know whether you took any electronics class. If you took the electronic class, you might learn the digital gatings: AND gate, OR gate, NAND gate, and then so on. So these, all those things, actually you can create any complicated circuit here, and then simulate that one to see whether you get in the real expected outcome or whether there are any problems, and then so on. So that this can be done anything like regularly you do with the oscilloscope. Only difference is that this is virtually still. Okay. Now in today's experiment, what we need, just very simple circuit. So let's create very simple circuit. We need a voltage supply AC, right? Just click and drag, and you can rotate this if you want to. When you bring the AC voltage, you can see a couple of things. AC voltage must contains the value right here. If you click that, you can put any letter, whatever you want to use. I'm going to leave it as a V1. And then if you click here, you can see you can change the voltage, right? So the voltage value right here is about 1 volt. You can click and drag this one. I can change this into 0 volt to 10 volt. And also we can go any number. You can go even beyond that. This is on 10 right here. You can change that to 100, 1000, and then 10,000, and then so on. So that's the other advantage. Unlike the in-class lab, I can do an experiment with the 100,000 or million voltage applied into the system. So that those are impossible to do in class setting. We need a very simple voltage. Okay, so let's do like maybe 1 volt. 1 volt or 2 volt, that's good enough. Okay, question. And also you can see here it says 1 kilohertz. So that's mean it is telling about the frequency, right? So if you have AC voltage supply, there should be a frequency. I can change the frequency from very small number, 0, and then 1 volt, and then so on. I can change that all the way to maximum number. Right now it's changing larger values, right? So the 750 and then so on. To change that, if you want to go with smaller values, that also possible. So I have to just change this one bit. Or I can type here whatever the number I need. I need just 1 volt, 1 hertz. Hertz is the unit I forgot to mention earlier. Hertz is the unit. If you measure frequency, that's 1 over time. So this is actually 1 over second. That unit we usually write it as a hertz. Okay, so that's a unit of frequency. It's just 1 over second, or second to the minus 1. Okay, question. Everybody okay with that? So that's our source now. So I need a resistor. So first we're going to do with 1 resistor. And then let's bring the switch to, because usually we apply a switch anyway for each of the circuit diagram. And then let's connect the circuit. And it is important when you do this circuit, let me rotate this one this direction. Okay, we'll leave it like that. So when you do this kind of circuit, usually this negative end, that's not really super important, but that should be grounded in most of the AC circuit properly. Otherwise, you will not see the result what we expecting. Okay, because of that, I'm gonna ground this end, negative end properly. And then if you want to connect one dot to the other end, you can see each of these endpoints has a dot, right? When you bring this cursor on top of that dot, that cursor change into this kind of circle. Then you click and then keep that click and then drag, you will create a line from one point to another. Then click again, then you create the connection. Similarly, this connection you have to click and then drag all the way to the other end. Then I have a connection there, and then I need to connect this one. Click and drag to the other side, other end of the switch. So I have a connection there. Okay, you have a switch. You can close the switch by clicking here, or you can open the switch by clicking there. Okay, so I have a closed switch to work this circuit. Okay. Now we have a circuit, and then circuit is working fine. Let's change the resistor also to a smaller value like 10 ohm initially. And now I have to measure this, right? If you take a look, this top line right here, there's a couple of selections. You can see now I'm in schematic, so that means the diagram. Then you can click the graphing, so to see the graph, and then you can click the both, right? So if you click the both, you will see the graph and the schematic together, okay? So that's my diagram. And then other side, you will see the graph. So that graph is actually my simulator oscilloscope. Oscilloscope front panel only, it's showing there. That's the graph, okay? Now you need to measure, right? If you want to measure, you have to bring the sensors, analysis and annotation. First selection tool, I need a voltage sensor. So let's apply the voltage sensor right here on positive side. Remember earlier I mentioned that if you're measuring through the voltage, you don't need to have a ground. So you just need to connect the positive. The grounding can be done internally automatically by the oscilloscope. So which means I'm connecting only positive end, okay? So other end is ground right here, which means this side. Number 2 line is grounded, okay? Number 1 line here is positive. So I connected my sensor into positive end right here, okay? All right, now all we have to do is to see the oscilloscope, you have to click this icon right here. It says run the simulation, right? After you finish the circuit, just click run the simulation. Now you will see on your graph, you see that line is going here and there. I expecting to see a sinusoidal wave, but I don't see that because you can see polarity change very, very rapidly. Now I have to do a couple of adjustment here. All the oscilloscope adjustment on here, right hand side, very top end, you can see an icon like a setting icon. So just click on that. It will open the configuration pane. When you have the configuration panel open, then you will see all the operations which the regular oscilloscope has. Most of the oscilloscope most of the oscilloscope operation you can actually observe here. Then number 1 is the trigger, right? Remember I mentioned that earlier. Trigger has to go auto. When you click the trigger auto, you can see that line now is stopped. If you put trigger into any other, none, you can see it oscillating, which means there's a wave, but wave is actually moving here and there. We can't see anything on the screen. So you have to first put it into auto. Now, if you have a digital oscilloscope in the real lab setting, you have the auto mode, you can put that. Only if you have an analog oscilloscope, then there's no auto triggering. Until you get this wave stop first. Now you can see, I can see only part of the wave. There should be a complete wave, but I don't see that, which means I have to zoom this in or out to observe that properly, right? Maybe I'm zoom in too much, so that's why I'm observing only part. So we have to go out, zoom out, right? You have to do that by actually changing these axes. I can change the value of x-axis. Remember that time per division value. And also I can change y-axis, that is voltage per division value, right? Now in your time axis, it says 1 millisecond per division. I have to change that, right? To change that, you can see here, time per division, right-hand side, this operation panel. So you change that. So you have to click this right-hand side, very top end. You see this small circle thing. So that circle thing is the configuration panel. So you just need to click that. It should be look like this. And you click that, then the panel will open up. Okay. And then you increase time per division. As you increase the time per division, now you can see, you can observe the full wave. But still, now I can see the wave properly. However, now there's a new problem. That problem is now my y-axis too much zoom in. So I have to zoom out that one too, right? So the y-axis zoom in and out, you can change by changing the maximum and minimum values, right? You can see maximum point now positive 1 volt. That is right here. That should be on axis. If it's not there, you have to click on the axis right here. You can see arrow. Just click on that arrow. That will open up this tool. So if you don't see it, it should say axis there. Okay, right hand side very below, you should see only axis. Just click on that. That will open up a tool. Now you can change the voltage values. Maximum voltage, it says 1. That is not good enough. That cut out little bit. Cut out little bit. The reason is my maximum voltage should be 2 volt, right? So let's do this like maybe 2.2. See that? If I do that 2.2, I can see the maximum very clearly. And to see the minimum clearly, I need negative, same number. Now, this is not this much easier if you do it with the analog oscilloscope. In class setting, we actually have both analog and digital. So we usually testing by using both of them in the beginning of the class to get the experience. And then later in the lab, we do it by using only digital oscilloscope. Okay, good. Anybody have any question? Everybody get that visible? So make sure your circuit is visible and then your oscilloscope is visible. All these operation tools, configuration tools are visible, okay? And now what we like to measure. What is your question? You can select actually all the information are just hiding right here. There are a lot of different selection tool. All you have to do is just click on the selection tool and then see whether it is hiding there, okay? So you can actually find it out. That's very simple. Just click on, for example, if you want to find the selection tool operation configuration tool for y-axis, just click on the y-axis here. Bring the cursor, click on there, then that will automatically appear. If you want to find the X, click on there, then you will get automatically that one. Okay, good. Any question? And also you can see this very right edge, there's a bar you can click and drag. If you don't see that on your screen, that maybe it's hiding below, okay? So you have to click that and drag. If it is look like that, which means that part is hiding because that voltage and time per division parts are very below right here, okay? You have to click that bar downward direction all the way to the end, then you will see the operation for X and Y axis. Okay, good. Any question? Now you just need to measure, really very simple idea. If you bring this cursor, you can see if you click anywhere on this screen, you can see that icon change into like 2 arrows and the dot. If you bring that arrow somewhere, anywhere on this curve, you can see that read a number, right? So that read 2 numbers. One number is x-axis, one number is y-axis. That's a coordinate, right? Because this is a curve, look like the graph, so you're reading the coordinates. So the x coordinate is time axis, time per division axis, and then y coordinates read the voltage axis, right? So let's bring it all the way to the top. If you bring it there, now you can see it reading the voltage 1.9970. That's the maximum voltage we expecting. That should be about 2. You can change slightly that location to see whether you can read the 2. If not, just take that reading. That is good enough. It is close enough. So that's the error. That's the human error. If you're doing these kind of measurements by using the oscilloscope, that usually the error, okay? And then if you bring all the way to the one complete circle right here, when it completing one cycle, so this edge right here should read the timer, that is 418 kilosecond, right? So that means 418 times 10 to the positive 3. You need to 1 over of that, and then that will give you the frequency. Now the frequency should be 1 hertz. Okay, makes sense? Following? Any question? And also you can read the time axis this way. Now you can see timer is 200 milliseconds per division, right? You take the 200 milliseconds per division, that means the value of one of this cube, and then how many cube on my x-axis? 1, 2, 3, 4, 5. So the 5 times 200 millisecond per division, that means 1000. 1 over 1000 will give you the 1 second. This is millisecond, okay? Remember, you have to multiply by 10 to the negative 3. That cancels out with the 1000. So you will get 1 second. That number is very accurate there. Okay, question. All right, let's go and take a look then. Everybody okay with this part? Can everybody observe this? Oscilloscope function and then all the oscilloscope configuration and the circuit. And if circuit working fine, you will see this voltage value right here. The sensor should have to show you two numbers are fluctuating because the polarity of this voltage fluctuating. So that fluctuation should be visible. And let's take a look then the lab manual. So the lab manual has a couple of sections, right? So let us start with the table number 1. This lab is very simple. There's no detailed calculation, no anything. Analysis part is very simple. You complete these tables and then basically you're done with the lab. Okay. Now you know how to do the operation of this virtual oscilloscope, simulated oscilloscope. As far as you get familiar with that, all the measurements are very simple. Okay, guys, any question? And also you can use another way to measure this one. You can put right here cursor, put the cursor into x-axis. Now, if you want to measure, for example, we'll say this point, that is the starting point to end point right here. That is my one complete cycle, right? So that complete cycle will tell you the value of the cursor number 1. Okay. So that's another way to measure that one. Now you can see delta x is 1.0017 second, right? So that's what we expecting, right? So that is a period of oscillation, delta x, bit value between the two cursors, C1 and C2. Now, similarly, if you want to measure y-axis, all you have to do, click on the cursor, change that into y-axis. Then you can see two cursors appear on y-axis, put the cursor 1 here on 0, bring the cursor 2 into right here to the very top edge. And if you bring that, it will tell you cursor number 1, cursor number 2, value between the cursors, that is about 2 volt. That is what we expecting, because this is my applied frequency and applied voltage right here. Same values I should be able to get from there. Okay, there's a lot of advantage when we working with the oscilloscope. All these measurements, these cursors, everything you can do with the real digital oscilloscope in class setting too. Okay, guys, everybody okay with that? Let's start then measuring table number 1, working on table number 1. So what we need, table number 1, we're going to be analysis sine wave, and then I have to change the frequency, measure the voltage, and write it down the voltage applied, and then measure the frequency at the voltage by using the oscilloscope, and then you have to draw what you're observing right here. Okay. That drawing going to be about the same. You can draw at least 2 diagrams. That's good enough. Or instead of drawing there, what you can do, you can take the screenshot here and take the screenshot of the observation. This whole thing is one screenshot, and this wave itself is one screenshot. Okay, 2 screenshot, and then wave itself you can add into here. Table number 1, column 3. Okay. So that's important because that tells you how you done the observation. Let's take a look what this asking on this table. Okay, guys, question. Right, let's working on table number one. Okay, table number one, what it asking, we analyzing the sine wave now, right? Sinusoidal wave, technically VAC type. And then on that table, it asking these things. Signal generator is actually in your simulator, signal generator is the power source. Technically, if you're doing this in class setting, this AC power source we're not getting from the power outlet or anything, right? There's a signal generator, it's a small item. It can actually make voltage with different frequencies. You have a lot of freedom of changing voltage, changing frequency, and also changing the type of wave. Like previously I mentioned you that you can change the wave type to like sinusoidal to like triangular shape or maybe square shape. All those variation you can do very easily by using the signal generator. Okay, so that's why in your lab manual it's telling signal generator here because of that. Okay, now these are signal generator values. So there are two columns right here to represent signal generator values, and then two columns right here to represent the values you measuring with the oscilloscope. These are given values, signal generator, and then this is the values you measuring from the oscilloscope. Okay, and then what we measuring is the frequency, unit of hertz, and then we measuring voltage peak value. This VP represent voltage peak. Okay, peak value represent if you have a wave that maximum point. Remember that earlier I mentioned the RMS and the maximum point, right? If you do RMS, that's going to be slightly less than the maximum. Okay, that's the idea. So we are not measuring RMS, we measuring directly the peak. But if you're using the real oscilloscope actually can tell you this both. It has an inbuilt function. You can ask to oscilloscope to show RMS value, or you can measure the peak directly. Okay, in your oscilloscope screen, you measure in the whole wave, which means this maximum point right here is the peak value. Okay, so we measuring right here peak value of unit of volt. Same thing, frequency from the oscilloscope, and then the voltage peak from the oscilloscope, and unit of volt, unit of hertz. And then you have to have a wave sign you observing. So you have to draw or put a picture here. I would suggest copy paste a screenshot of one of the circuit with the result. Okay, good. Any question so far? Then let's continue. So measurement, what we have to do, voltage, we can keep 2 volt. We don't need to change the voltage at all. But let's take a look how to measure the frequency as we continuing. Okay, and then let's start with 2 volt, and then we have to start with 10 hertz. So that means you have to click here and then change this into 10 hertz, right? Easy way is actually just click on that icon there and then type 10. That will give you 10 hertz. Now, if you have that, you can see immediately everything is changes on my screen, right? So that means there are many waves. So I have to change that little bit, right? You can change that easily. You can change that easily if you change the x-axis, right? Just click on the x-axis and then go on your right-hand side configuration tool and then change the x-axis. Increase, decrease division per second value now. Now at some point you will get a nice curve observable, then you stop there. So those are the operation you have to do manually if you're doing this in class. But the oscilloscope virtual one is very simple. You just need to click and then it will show you everything. And trigger should be always on auto mode. Okay. All right, now let's continue this one. So I need to measure voltage now. Voltage, I apply 2 volt. I have to measure frequency and voltage by using oscilloscope. Let's continue this. We are on 10 hertz. Let's say 10.0. Voltage apply is 2.00. I have to measure these two, right? By using oscilloscope. So let's do this voltage since my cursor is already there. Right hand side, you can see the cursor. If you click on the cursor, right here, you can select whether you need x-axis, y-axis or none. If none there's no cursors visible. You can click the y-axis cursors. Then right here below the graph sheet, very edge point right here, you can see value of cursor number 1. That should be actually 0. You can try to get it into the 0, but it will be very difficult to do that. So get it into the 0 line as close as it is 10 millivolt, that almost like very close to 0, right? 10 times 10 to the negative 3. So let's take that number. That's okay. That's our human error, right? There are always going to be some sort of error. We'll use that error. And the cursor number 2 should be at very top edge. That should be a 2 volt, but you can see I can't really get it into that 2 volt. Just leave it like that. It's very close. That's good enough. Then the difference between them, 2.0074. That's the answer I need here. Now this number is 2.0074. Now you can see that's slightly off than the value I expected. That's okay. That's the error we expected. And then let's do the cursor for x-axis. First one should be at the starting point after it complete one cycle. Second one should be after it complete. Difference between them 100.17 millisecond, but I don't need actually time. I need the frequency, right? So I need technically here 1 over 100.1 second, 17 millisecond. Milli is 10 to the negative 3. If you do that calculation, you should get the right frequency what you expecting. Make sense? So do that calculation in your calculator and then see what you get. Number very close to 10. Not we doing something wrong. Okay, guys, following any question so far? So let's calculate that. So what I need 1 over 100.17 times 10 to the power minus 3. If you do that, you will get 9.9830. Since I can read all the way down to 5 sig fig, I'm going to use all, okay? 9.9830, 5 sig figs, okay, right here. 5 significant figures, right here, 5 significant figures. If you do any reading with any measurement, any instrument, you have to write it down every visible reading there, okay, every visible significant figure. Now you can see expected results are slightly off, right? Now these are the real values which I include. And now these are the values which I actually observing, right? You can see these numbers are very slightly off. If you do the percentage error, you can see maybe like less than 1% error. That's the human error. So now this error happening even with the virtual oscilloscope, which means if you do in real class setting, you have to be really careful when you do this measurement. But actually real class, this is much easier to do because these cursors, I can move very, very slowly by rotating a knob. So because of that, it's very easy actually doing this measurement. It's not difficult at all. Even easier than this virtual case. Okay, question. No question? Everybody okay with that measurement? Okay, now the rest of the measurement in that table, all you have to do now, what it asking, change the frequency into 100 and then do the same observation, change the frequency into 1,000, 5,000, 10,000, 50,000 and 100,000, and then do the same observation. Okay, so let's continue. So I will let you to measure everything. Write it down. The voltage will keep the same. That is easier. So let's don't change the voltage at all. Let's keep the voltage is same. Let's do next 100.0 and then next 1,000.0 and then so on. Okay. And then 5,000 and 10,000 and then 50,000 and 100,000. Okay, let's do 100. To do 100, what you need is change this frequency. Click on there, just type 100, hit enter. Now you will see again the lot of waveform appear. So all you have to do, click on the x-axis, change the x-axis until you see a nice waveform. Now I have a nice waveform. That's it. Then you can read the data. So already two cursors are there for X. So I'm going to read that. That is 10.017 millisecond. So let's read that directly. So my time is already there. That means 1 over 10.017 milli. Okay, 10 to the negative 3. You do that calculation. Find the frequency there. Voltage applied. I keep it same 2 volts. Let's read the voltage. All you have to do, change the cursor to y-axis. Now you read the difference between the two cursors, 2.0074, because that remains the same. We did not change any difference there, 2.0074. And then likewise you continue. So then you change this into now 1,000, right? Next one, 1,000. And the x-axis, I have to change this until I see nice curve. Change the cursors into x. Difference between the cursors 1.0017 millisecond. Now you can see there's a problem, right? Because this millisecond, you can see it does not change at all. However, if you go with this right hand tool, selection rule, time per division, it says difference, the scale should be 200 microsecond per division. Due to some reason, you have to be careful when you're reading. This different delta x given as a 1.0017 millisecond, but that unit is not updated. That something to do with this simulation. You have to be always vigilant. Real unit should be 200 microsecond per division. Okay, so you have to use the units accordingly. So I have right here 1 over 1.0017, but not milli. Instead, you have to use 200 microsecond per division. Okay, so that's the right one. Make sense? Follow me? 200 microsecond per division. So let me write it down, that part here, a little bit clearly. Okay, so the frequency is 1 over time. So the 1 over, I have unit 200 microsecond per division. How many number of division? 1, 2, 3, 4, 5. Okay, 5 divisions. Make sense? So do it that way, then you have actually right. Now it is actually updated properly, I think. Now it's fine. Now it says 200 microsecond per division. Okay, make sure you check that number right here and the number in your selection tool. Okay, operation panel. Because sometimes this x-axis unit does not update properly, then you have a problem there. Now you find. So if those two are updated, then you will get a right number. So this you have to do the calculation. 1 over 200 times 5 is 1,000, right? So which means 1,000 times micro is 10 to the negative 6 seconds. So if you do this calculation properly, you will get the frequency. Okay, 10 to the negative 6, 3 cancels out, 3 will remaining, that 3 comes to the top, you will get the 1000. So that's the right number we expecting. Good, any question so far? Everybody okay with that? Now this number is fine, okay? 1.0017 millisecond, that also fine. You can use that directly. 1.0017, 5 significant figures, milli is 10 to the negative 3. Okay, let's do 5000. So click here, put 5000, hit enter, and then click x-axis, change the x-axis little bit until you see it properly. Okay, I need to have a complete loop and then bring this second one all the way to x-axis. Okay, good. And then now my delta x is about 199.83. So now we're doing this part. Frequency is 1 over 199.83 times. Now it is microsecond. Okay, micro is 10 to the negative 6 second. So you do that calculation, then you should get the right frequency then. And then so on. I'm measuring only frequency because voltage value does not change at all. Okay, since we're keeping the voltage, every time you change this into y-axis, that will tell you the same voltage. See that number, 2.70074. Voltage remains the same, 2.0074, 2.00, 2.0074, 2.00, 2.0074. Let's do this with 10,000. 10,000. 10,000 and then change the cursor into x-axis. You can see y-axis doesn't change at all, okay, because we did not change in the voltage. X-axis, you change this until you see nice full curve, and then change the cursor number 2 until you get the complete curve. You have to carefully change all the way until you bring that all the way to the end of that curvature, okay? So end is right there. It's going to be slight error always. That's okay. That is our reading error. Now the difference between the two cursors are about 99.756 micro. So this is going to be frequency 1 over 99.756 micro 10 to the negative 6 second. Calculate that. That will give you the frequency. And then so on. Okay, question. Anybody have any questions so far? Okay with that? You can do this in your Excel page, right? If you have Excel sheet set up, this calculation will be very easy to do. Okay. All right. And then beyond that, you need 50,000 and 100,000 for table number 1. Let's continue. So I need 50,000 frequency, and then voltage we are not changing, 2.00, observed frequency, and observed frequency, and then observed voltage, or observed voltage will not be changed at all. Observed frequency going to be 1 over the time. So let's take a look. So let's change this into Now 50,000, 50,000, hit enter, and then change the x-axis scale until you see very nice visible curve, full wave, and then change the cursor number 2 all the way to the end point of the one wave. End point of the wave, whole wave is, it should go into positive side, come back to 0, go to negative side, come back to 0. That's the complete wave, one period of oscillation, right? So now the difference is 19.983 microsecond. So this is going to be 19.983 times 10 to the negative 6 second. You take that answer, that will be the frequency for the 50,000, and then you do 100,000. Voltage doesn't change at all. Voltage measured should not change at all. And then let's do 1 over time for the 100,000. All we need is to change the frequency into 100,000. Hit enter button, and then change the x-axis values, and then make sure those are changing, and then this number is updating. Okay, you have to check the both, otherwise our reading value right here will not be accurate, because the simulator has a little bit delay of updating these axis units. Okay, please take a look. Axis unit should be matched with the time per division value on your right hand operating panel. Okay, then we are fine. Now the difference I need, let's increase this little bit and then change this one all the way to the very end. And then the difference now is, now you can see this is not updated yet, right? This is 5 microsecond per division. This is 2. So I have to wait until it updated. If it not, we're reading wrong. So that's a problem. Okay, you have to always check that. If it's not updated, so we're reading it wrong. Make sense? Following? Good. So that unit is not updating, but my delta x is updating, I think, properly. Let's see why it is not updating. It has a delay actually. Sometime if it's not updating, we have to read it manually. That's okay. It seems to be not updating at all. Let's read it this way. Change it back into 2 microsecond per division. Now, since it is not updating, you can't read this number right here on the bottom directly. Instead, what you have to do, read the how many number of segments in between the cursors, 1, 2, 3, 4, 5, and then 5 times 2 microsecond. Okay, we have to read it that way. Make sense? Following that? And also delta x value is given here directly. That number is also you can read directly. Now this is 1 over delta x. That is the frequency, right? So that number you can check with the applied value. So this is about 100 kilo. It should be 100 times 10 to the 3. So that is about 100,000 hertz, right? So you have the right answer then. Make sense? Following? 100 times 10 to the positive 3 is actually 100,000 hertz. So we have the right answer there. So which means it's going to be 1 over 10.004 times 10 to the negative 6 seconds. Okay, question. We're done with the table number 1. So make sure you take the screenshot of the first circuit, and then you have to do the same measurement, table number 2. Table number 2, exact same measurement. There's nothing changed. You have to do that with the square shaped wave. Okay. So that's the only difference. Top of the table, it say use the square wave. So to do the square wave, what you have to do, you have to go to your simulator, and then you have to change this voltage, right? To change the voltage, you have to first stop the simulator running. So click the stop button. When you click the stop button, you can see the left-hand side selection tool will appear. Get rid of this voltage supply. I don't need the sinusoidal wave. Instead, I need the square wave. Click on the sources and then bring the clock voltage. It should say clock voltage here. Click and drag. So that clock voltage is actually the square wave, okay? And let's change the voltage into 1 volt or 2 volt. That's good enough. And the frequency, let's start with about like 10 hertz. Okay, and also you can bring a switch. Since the switch is already there, you can leave it like that and then connect this one directly. You know how to connect this dot. Click on that very end. Then it will appear like the circle. Then connect that into the next point. Click there and then connect this end. Click and then red wire and then connect into the other end. Okay. Now it says this voltage sensor says out of date. The reason is now we changed the circuit. So we have to rerun the circuit to see the right values, right? So now voltage is 2 volt, frequency is 10 hertz. All you have to do is click this run button right here on the top. Then you will see it will update automatically. Now you can see it updated, but nothing is visible, right? So I have to redo the adjustment. Trigger should be auto. And then couple of adjustment we have to do. Okay, so let's click here. Okay, following. Any questions so far? Everybody okay with the table number 1? Anybody have any problem with the table number 1? No problem? Okay, now to change this, so now you can see the wave, right? So you have to change the time per division until you see the clock wave. Clock wave is like this square wave. And then put the minimum into minimum into 0. One quick thing actually you have to do here. So you can see when I connect the circuit right here, the source positive connected into the ground. So that's not correct. So please change that. Otherwise you will not see the right shape. Okay, you need to rotate this. Let me do this. First we'll get rid of this one and then bring it back. Otherwise circuits look ugly. So you have to have the nice looking circuit here. So rotate this one until positive is on to your left side. Okay. Then start connecting. Voltage, put it back into 1 volt. And frequency, put it back into 10 hertz. Okay, now let's connect these two end again. That's why our circuit diagram earlier, the wave looked like not normal. The reason is actually this endpoint should be connected properly. Okay, now it says out of date again here. Reason you have to run the circuit. Okay. All right, now we have the right circuit. Now you can see everything is nice and then the positive wave should be visible. Good. Now all I need is in this case voltage again we're not gonna measure continuously, right? Because voltage we're going to fix, only frequency is actually we changing. Okay, same concept which we done earlier, exactly same numbers. You need to take the picture, screenshot, and then we're going to do the same measurement. Okay, so let's bring this curve right here, voltage, let's put it into 2 volt, right? So that maybe match with the previous values there. Okay, 2 volt, now it's good. Between two cursors, right here it says 2.0074, that's our reading error, right? So that will be there. So let's go into x-axis, and then change the cursors into x-axis. And then you can see now between the cursors, it says 100 millisecond, 100.00 millisecond. And the 1 over delta x, 1 over time, is actually 9.0065, 9.9965 hertz. So that is actually the direct frequency we apply, which is 10, right? Close enough. So you just read that directly. Now this part, since we already know how to do the calculation earlier, you don't need to do in the calculation again. Let's do table number 2 in easy way. Table number 2, let's do the calculation directly. Okay. So the table 2. Any questions so far? Everyone okay with the table number 1? Any questions so far? You have to read all the sig figs. So the simulator will give you 5 significant figures, right? For each of the value you can see 5 significant figures, read all of them. But the given values, you don't have that much here, right? So you have only like 2 volt, just one significant figure, and the 10 hertz, one significant figure. But let's write it down with at least one more significant figure. But the reading values, use all, okay? Table number 2, we have a square wave input signal given like this. Square wave, either switch on or switch off, right? So that's the clock voltage. So that called the clock voltage, either switch off, this position is switch off, this position is switch on. So again, this changing, right? Switch on and off changing. So I can set up the frequency. If this is the starting point, you switch on, keep it up, off, keep it up, and then switch on again. You complete one cycle, then take the period of that cycle. That is the delta x we measuring on our x-axis. That is the time, okay? Then you take the 1 over that time, that is the frequency what we call the hertz, okay? So now that number we're going to read directly. We're not going to spend time on calculating that. You know that how to do the calculation. So the given values, that's the signal generator values, right? Signal generator values, and then observed values from the oscilloscope. Observed values, that's the oscilloscope values. And then the picture here, that's a diagram, okay? So what I need is the frequency in unit of hertz, and I need the voltage peak value, unit of volt, and then the frequency observed, unit of hertz, and the voltage peak, unit of volt. Now this number we're going to keep it 2.00. This number will be same like that. We don't need to remeasure again. Only thing we're going to measure the frequency. Now let's read the frequency directly, since you already know the calculation. It actually right here, right? 1 over delta x, 9.9965. So the value here 9.9965. There's a small reading error, right? So that's okay. So you can see we expecting 10, but we're getting 9. So that's totally fine. So we are in the limit of error. Okay, margin of error. Okay, all you have to do now is change the frequency again, right? So let's change the frequency. We started at 10, then we go 100, 1000, and then so on, right? Let's change this into 100. Hit enter button. And now you can see You have to change the x-axis again, right? Time per division to see nice wave, right? It's not really nice there. So to change that, click on the x-axis and then click and drag this right-hand side bar and then change this number right here, time per division value, until you see nice one single wave, okay? Okay, now we have the right everything properly. The y-axis we don't need to remeasure again. You can check always, okay? Y-axis should be the same delta y. You can see 2.0074. That's the peak voltage. And the x-axis cursors will tell you 1 over delta x, that is 99.965 hertz, but we're expecting 100. That's okay. That's our margin of error. So we have 100.0, 2.00, and we expecting 100, but we getting 99.65. What's the number we getting? 99.965 hertz, right? Let's read that directly. 99.965. This number doesn't change at all. And then you continue this one. And we need next 1000, right? And then we need, let's do all the values, 1000, 5000, 10,000, and then we need 50,000, and then we need 100,000. Okay. Extra one significant figure for all of them, one decimal place for all of them. Let me share this. All you have to do, change the frequency, right? Let's click on the frequency point here. I need to get now 1000, right? And one more zero there. Hit enter button. That will change automatically. And to get this x-axis operation, you can always click on the x-axis division per second point. Just click on there on top of that. Then the operation panel will appear. And then go downward right here, right hand side very edge. And on the operation panel, click towards your left. More and more smaller time per division values until you see nice one complete curve, right? Then at that point, read 1 over delta x value. Now I am on 1000. That telling me the value is 999.65. So that's the number we need. So let's read that number and then write it down here, 2.00 999.65, and then this does not change at all. And likewise, you continue this, and now we are on 1000. We need 5000. Again, I have to change the x-axis. You can see because you adding more and more frequency mean a lot of wave within short period of time, right? That's why you see smaller here, which mean you have to increase or zoom in your x-axis more and more, right? So that's the idea. So let's do that until I see nice single wave on my screen. Is that too much? A nice single wave. Now you have to bring this cursor number 2 all the way to the end, right? End of the wave. Okay, right there. And then my value is about 4.9869 kilo. That's mean about very close to 5,000, right? So that's good. So then you continue likewise. So it's not really anything big deal. It's the same measurement, right? Voltage keep the same. Now this is 4.9869 kilo. 4.9869 kilo means you can actually write it down with multiplying by 10 to the 3 or 4.9869 times 10 to the 3. So it is about 4,986.9 hertz, right? That's very close to 5,000. So we have a small error. That's the reading error. So this is not changed at all. And then you continue likewise. So I need now frequency 10,000. Frequency 10,000. And change x-axis, time per division. Okay, so until you see very nice curve, and then you click and drag this cursor number 2 all the way to the very end, right? And then you read the new value. So that is 9.9410 kilo. So that means that is 9,941. So that is slightly off. So you can little bit adjust this cursor number 2 to see whether you can get almost very close to 10,000 hertz. If not, read the closest value possible. Okay, that's okay. That is the human error, right? So that is our reading error. So that always the case if you're doing this in class. So you will get some error anyway. So I'm going to read this number. That's okay. 9.9410. So this is 9.9410 times 10 to the 3. These numbers are not changed at all, right? Remains the same. Okay, now I just need to read these two, right? So you just need to change your frequency into 50,000. Now, if you're doing this as an experiment in a circuit, you can see you can switch on and switch off 50,000 times per second in that circuit. That's the idea, okay? That's the idea of frequency. So 50,000, hit enter, and then you have to change again x-axis. Click here. Let me know if you have any difficulty doing any of this operation. Usually this should work fine with any computer because it's working on the web browser, nothing to download or anything. So should not be any problem at all. Okay, anybody have any problem so far? Everybody okay? Good. So the frequency is 49.869. So that is very close to 50,000, right? So that's the idea. 49.869. This is now 49.869 times 10 to the 3. And then let's do last one, 100,000. 100,000. Let's change this value, the cursor point. Since it is visible, I'm going to leave it like that. And I'm going to change only the the cursor value, cursor position, all the way to match with the very end. And now you can see it is 100 kilohertz. That is actually 100,000 hertz, right? So 100.00. 100.00 times 10 to the 3 hertz. Okay, and then you have to have a diagram here. Okay, copy paste a picture from that diagram. Okay, circuit diagram. Okay, question. So table number 2 is then table number 3 is exactly the same thing. What we're going to do, we're going to connect couple of resistors together, and then we're going to measure voltage and current by using the sensor, and then we're going to validate the Ohm's law. That's the plan actually. The next few labs, this lab and next lab, what we actually doing, what we done previously, we're going to do the same experiment with the oscilloscope. So today's lab, we measure in the we test in the Ohm's law by using the oscilloscope measurement. Next week Monday lab, not next week lab, this week Wednesday lab, we actually doing the RC circuit, charging discharging circuit with the oscilloscope. And only next week Monday lab is the completely new lab. We're going to analyze the RLC circuit, the oscillations of that circuit. Okay. All right, guys. So any question so far? Everybody okay with that? All right, so let's take a quick break and then we'll continue with the table 3. I think we can finish before 11 and then last hour we'll continue with the last chapter, okay? So let's take a break, 10, 11 or so, and then let's take 15 minutes, okay? Let's start. All right, anybody have any questions so far? Then let's continue table number 3. So on table number 3, what we're going to do, we actually analyze in the Ohm's law technically by using the oscilloscope. Okay, that's the plan. So I have to connect, I have to create this circuit. Okay, I have to create the circuit serially connected 3 resistors. So let's do that first. So I need 3 serially connected resistors. Okay, so let's, if you want to do any changes, you have to first stop this circuit, right? So the running simulator, first stop that. Then I have to bring another 2 resistors, right? So let's disconnect this one. And also we now need again the sinusoidal wave, right? Get rid of the voltage supply and also disconnect this one too. And then let's bring 3 resistors, resistor number 1, resistor number 2, resistor number 3, right? I need 3 resistors, 3 resistors. Okay, and the values of the resistor should be 15, 45, and 65. So I need first one to be 15, 15, second one to be 45 ohms, and third one to be 65 ohms. Okay, so we have that, and let's separate this out a little bit, the resistors, separate this voltage sensor a little bit. Okay, then let's connect. I need the voltage, new voltage, AC type voltage. And let's rotate this one also to be positive one to your left, okay? So then otherwise you will not get the right output. Okay, let's use voltage supply since it is not given any numbers. Use the frequency fixed number, voltage value also fixed. We're not going to change both of them. So we can change the voltage value maybe about to like maybe 2 volt. That's good enough. 2 volt. And the frequency you can keep it to like maybe 10 hertz. It's not really matters at all. So we're gonna test the Ohm's law. That's all really. And then connect this. Click on the corner and then connect the circuit. Okay, follow me. Okay, connect all the segments between resistors. Okay, so that's it. Then I need to measure voltages across each resistors, and also I want to measure current, right? So I have one voltage sensor here. So leave it just before R1. Then bring two more voltage sensors, one between R1 and R2, another one between R2 and R3. Those three actually measuring voltage across R1, R2, and R3. And then I need the current sensor. So the current sensor, you have to place it somewhere on anywhere on the circuit. It technically doesn't matter. So that will tell you the current because it's a serial circuit, right? So the somewhere on the circuit, place the current sensor. So that will tell you the current. Okay. And all you have to do, then click run button. So if you click that run, then that will tell you the voltage across each voltage. You can actually use many voltage sensors or one voltage sensor. It doesn't matter. So let's use one first and then see whether I can change that accordingly and then measure voltages. Okay, let's measure one voltage sensor and then measure across each of the resistors. All you have to do if your circuit is complete, click the run icon. That will brings you the simulator back. And then you have to rearrange little bit all of these things, right? So basically there's no wave now because my wave is almost zoom in too much. So if you zoom in too much, wave is there, but it is not visible. So you have to make it visualize, right? To make it visualize, you have to actually zoom out a little bit. If you zoom out a little bit, then you see that visualized wave. Now you can see two waves, right? So the green one is the voltage sensor. Now this pink color one or the violet color one is actually the current sensor, right? So you have two waves now, not one wave. Now both waves has about the same frequency, but you can see the values are different. So if you click on the y-axis left-hand side, that is the voltage values, and then y-axis right-hand side, that's the current values. Okay. If you click on the right-hand side and then change the current values little bit, now the maximum is +1. That seems to be too much zoom in. So let's try this with the 0.1 to see whether I can visualize that. That is visible, but it is not, I can zoom in more actually if I want to, right? So you can go a little bit further, maybe like 0.05. Yeah, that's better. Now it is visual. Okay, now you can see both has the same frequency. Okay, you can see one complete circle cutting exactly at the same place, but is inverted, right? Inverted mean you can see current actually I put it in opposite direction, right? Because the regular current direction should be positive to negative. So if you click this and then place it somewhere on the, I have to stop this for a while if I want to change anything. And then let's place it somewhere in the middle and then let's run it again. You see that? Now everything is fine. So the current is positive, voltage is positive, right direction, and then the current and voltage curves, you can see red, this pink and then green value, green curves are cutting exactly same place on x-axis, which mean those are actually called the in phase waves. In phase mean phase is on the same way on the both of them. Okay. So the oscillation frequency is exactly the same. That's the idea of in phase. So the x-axis should be cut exactly at the same place. Now let's measure. So this one we're not interested in analyzing sine wave or anything. What we interested is measuring voltage and current across each resistor, right? You need the circuit diagram again. So the copy paste the circuit diagram into here, a small picture. And then on third column, you have to measure voltage and current between each resistor. And then you have to calculate that, okay? Calculate the resistance value by using them. Let's do that. So now voltage across each resistor you can measure by using the voltage sensor, right? The current is the same. You don't need to have the current sensors moving because it's the same line everywhere. The current is same, right? You can see that the polarity is flipped and the change is actually, the number is changing on the sensor, but we are not reading the sensor. You have to get the values from here, okay, on the curve. All right, so let's take a look at that part. Any questions so far? Everybody have the circuit correctly? Good? Any problem? So the simulator, this is the same simulator we're going to use this Wednesday and next Monday. Okay, next 2 experiment going to be by using the same simulator. You have to really get practice this. Okay, how to use that. That's why I spent a lot of time today to explain everything and then do everything very slowly, hoping that you can actually learn that better. Okay, anybody have any questions so far? Okay, so let's take a look now. You have a circuit diagram look like this: 3 resistors, resistor 1, resistor 2, resistor 3, and then 1 AC current and 1 AC voltage and the switch. When switch on, current will pass through here, and the current we measuring by using the current sensor, voltage we measuring by using the voltmeter, R1, R2, R3. Now, what's the question is really asking whether you can calculate these R values by measuring the V and I, right? You can do that because you know Ohm's law, which is V equal IR. R value I can calculate by measuring voltage and the current. So that's a very simple idea. So which means if I measure voltage across each of these resistances, right? This voltage is going to be V1, this voltage is going to be V2, this voltage is going to be V3. So I can measure R1, which is equal V1 over I. Current is same, right? Then the R2 gonna be V2 over I. Then R3 gonna be V3 over I. Then we're gonna compare these measured R values or the calculate R values directly with the known one. This should be 15 ohms. This should be 45 ohms. This should be 65 ohms. Okay, that's the plan. Make sense? So let's continue then. Let's take a look first the current value, right? Current value is constant, which means if I click here on the current axis, and then if I go into cursors, I need the cursor on y-axis, put the cursor onto y-axis. And then right here you can see now, because I have two channels now, right? Because of that, the cursor you have to select accordingly. Okay, there's 2 channels. So let's select the channel number 2. Channel number 2 cursor you can see becomes now the same color, right? So I need the cursor 2 also in the same channel. Let's see why the color is not changing. Yeah, so the simulator, due to some reason, it becomes a little bit slower response. Take a look, maybe depending on your computer, okay, sometime it can stuck. Sometime you have to refresh the whole web browser. So those things you have to sometime little bit, observe carefully, okay. If it becomes non-responsive, so maybe if you refresh the whole web browser, it might be working fine, okay. Or if many things running on your computer, sometimes the whole computer can become slow response. So that something you have to carefully observe. So now I need to measure the current. So the current value, to measure the maximum value, you can just bring this cursor number 1 all the way to the maximum place, because we interested only that number, right? So if I measure that, the maximum point, so that's about like 15.841 milliamps. So that's the current value, 15.841 milliamps. Let's measure the voltage. Measure the voltage now. If I use the voltage sensor right here, that measuring the total positive voltage, right? That is not what actually we need. We need the voltage between these this resistor, right? Which means technically I need the voltage across this resistor. I need the voltage on right hand side on resistor number 1, and then voltage on left hand side resistor number 1. I need the difference between them, right? Let's bring another sensor, another volt sensor, and then place that after the resistor number 1, and then let's read the both values. Okay, now run this again. Now you will see 3 curves on your oscilloscope. So the pink curve is actually the current that we already have the number. Now you can see green curve and the blue curve, right? We don't need any of those curve values directly. What you need is the value in between. So the value between the blue and red curve, right? The difference between them. That is the voltage across our number 1. Make sense? Follow me? So let's read that. So if you read the green value, that should be 2 volt because we apply the 2 volts. You can see cursor number 2, 1.9975 that we have. Now you can see I have multi-channels, right? So I have 3 channels. So I'm gonna change the cursor. Cursors you can get only 2. You can't get more than 2 cursors. You have to change the cursor number 1 now again to channel number 4 here. Let's do that. Cursor number 1, V1. So I need V2, channel number 2. Okay. Now rearrange this one. Now you can see the cursor color is changing, which should change automatically. Okay. So let's bring the green one again, top of the green curve. That should read close to 2 volt. 1.9975, right? And then bring the light blue one on top of the blue curve. Top of the blue line, that is about 1.7639. So now if you get the difference between them, take the difference between them, calculate resistor R1. Resistor R1 is equal voltage across resistor R1 divided by the current. Okay, you remember we measured the current earlier. So you have to note it down on your table. Okay, table asking you right here voltage and current across R number 1. Let's take a look the voltage first. 1.9975 minus 1.7639. And divide by the current. So the current value is actually this pink line, right? So that you can measure the maximum value just by bringing the cursor onto the maximum point that actually tell you the maximum value, or you can change the cursor, one of the cursor. I have actually only 2 cursors, okay? I can't have more than 2 cursors, so which means I have to change one cursor here into current. Right, see that color changes, right? Cursor number 1, then you can bring that cursor on top of here. You have to slowly adjust until you reach the very top of the curve and then read the maximum point, 16.018. and milli, okay, times 10 to the power minus 3. If you do that calculation, you will get the resistance value 14.58. That's close enough. I mean, we have some reading error always. So let me write it down, all of those in your table. Okay, so now we are working on table number 3. So the column number 1, R values, right? R1 is 15 ohms, R2 is 45 ohms, R3 is 65 ohms, okay? And then accordingly, you have to put a diagram here, okay? So the circuit diagram, picture of that. And then here you have to measure voltage and current for each of these, right? Voltage and current for each of these. Current is same, right? So let me write it, take more space here. So the V across R number 1, V1 is actually different between these two voltage values. 1.9975 minus 1.7639. That's the voltage across V1. And the current passing through there is actually same, 16.018 times 10 to the negative 3. I need the SI units, okay? Then you calculate that R value right here, the calculated R1, which is equal V1 over I. So if you do that calculation, you will get 14.58. 14.58. Since I can measure everything into 5 significant figures, let's do 5 significant figures, measured value 14.584. So you write it down your values, okay? These values should not be the same as mine, because depending on how you place your cursor, these decimal places should be different. Each of you should observe the different decimal places, okay? There's no reason to get same values. That almost impossible, because this cursor I can change by click and drag to all the way to this top point. As a result of that, you all should get a different decimal places, okay? Should not be the same. That's all. It's a very simple calculation. If you do all the calculation correctly, you will get the Ohm's value result. Then you compare this with this guy. So that means percentage different here, PD value between 15 minus 14.584 absolute value divided by, it asking PD absolute value divide by average of that. So you know how to do the percentage different, right? So 15 plus 14.584 divided by 2, everything absolute value multiplied by 100. So that's the percent different for the resistor R1. Then you do the same calculation for R2 and then R3. That is for the circuit number 1. Okay, good. Any question so far? Let's do the same calculation now for the R2. That means I need the V2, right? To get the V2, you know what you have to do. Now you have to change this voltage sensors. So which means you have to first stop the simulator. That's why earlier I mentioned, instead of stopping the simulator at a time, you can actually use many voltage sensors if you want to. Doesn't matter, because this is a simulator, you can get many. But let it stop here and then move this voltage sensor between R2. So that means one voltage sensor there. I'm going to move this current sensor a little bit away and then bring the other voltage here. Okay, since actually we already know the voltage in between, you already have that value, you can use that. But instead of measure this again. Okay, you can see current value should not change at all, 16.018. You can keep that as it is. voltage. This green one now represent voltage in between. You can see that is 1.7639, the previous number. Now after that, that's the blue line, I have to remeasure, which means the cursor I have to change. Click on the cursor. I have to change the cursor number 1 to voltage number 3. Okay, check the color. Okay, but you can easily identify by looking at the color. Move that slowly to the end of that. Okay, right there, and then read that value 1.0474. Then you do that calculation. So how to do the calculation? So I need the V2. V2 is actually now voltage between the green and blue, right? So the green value is the same previous number, 1.7639 minus blue value is the new number. So that I already have it here, 1.0474. 1.0474. That's the V2. So you calculate that one. I is doesn't change at all. 16.018 times into the negative 3. Take the ratio between them. That is actually the R2. R2 should be V2 divided by I. So that number should be about the same as 45 ohms. Okay, if not, either you're doing some calculation wrong or your observation is incorrect. Okay. So which means still you can see this is now AC voltage. We are not using DC voltage any longer in the circuit. It's still the Ohm's law is still valid, right? As far as we measure everything carefully, we should get the right answer. Let's do the calculation. What we have 1.7639 minus 1.0474 close parentheses divide by 16.018 times 10 to the power negative 3. If you do the calculation, I'm getting 44.731. That's close enough, right? 44.731. We're going to use 5 significant figures because you can measure everything to 5 sig figs. Okay. We are solving for resistance right here. That's what we're doing. Next column. That's what we're doing on the column number 4. That's what we're calculating. We are using 5 significant figures. Okay. Good. Any question so far? So that's what we're doing, right? There's there's 1, 2, 3, 4, 5 columns. First column given numbers. Second column is the circuit diagram. Third column, you measuring voltage and current across the resistor. Fourth column, you calculating the resistor by using the Ohm's law. Then fifth column, you're doing the percentage difference between calculated and measured resistance value. That's what we're doing. Okay, very simple calculation. You done the Ohm's law very long time ago, few weeks ago. Now we check in the Ohm's law again at the very close to the end of the semester, but now we have the AC voltage. Okay, now we're doing again the percentage different. R2 given, that is 45 ohm. R2 calculated by using measured values. Now I am getting 44.731 ohms. Now you compare these two, that's the percentage difference. Then you do the same thing, exactly same kind of calculation for R3. First 2 column, the third column you actually calculating V across the resistor number 3. You have to measure the V across resistor number 3. Okay, to measure V across resistor number 3, I have to change my sensor again a little bit. So we're going to stop the circuit and then move the sensors. Now sensor green one and the blue one. This one should go all the way to the end. And then this one should come here. Okay, then let's run the simulator again. And then you will get the new voltages. Right now you can see voltage sensor, this blue one, which is connected to the negative end of the circuit, right? That should be 0. You can see that on this curve, right? So the blue line is on 0 level. That is reading 0. So only I have to read this green line. So if you read the green line, cursor number 1, so that value is 1.0474. That is the voltage across the resistor R3. So that measurement is fairly straightforward and easy now. So the V3 is 1.0474, 1.0474 volt, and then I is the same, right? It doesn't change at all, 16.018, but milli amps. Then you take the ratio between these two, calculate the R3. So that's going to be V3 over I. Okay, that's the calculated value. So if you do that calculation, you will get 1.0474 divided by 16.018 times 10 to the power negative 3. So you will get 65.389. 65.389 ohms. So now you compare that 65. This is R1 real value we expecting to be 65, but sorry, R3, but R3 calculated value from experiment we getting 65.389 ohms. So you compare those two to get the percentage difference. Okay, question. Now, beyond that point is actually very simple thing to do. All you have to do on your table number 2, you can see there's 2 other circuits, right? So all you have to do, build those circuits, right? So the next circuit is asking R1 and R2 serial, R3 parallel. If you take a look, these are the same circuits which we built on, I think, experiment number 3. Experiment number 3, when you do the Ohm's law analysis, these are the same circuit we built there, okay? It's not really anything new. We analyzing by using a oscilloscope. So you stop the circuit first. Now you have to rebuild this circuit. So I have to break the everything first. Let's break all these connections. Now you can see R1 and R2 should be serial, but R3 should be parallel to that, right? So let's take a quick look. Make some space here. Okay, now bring the R3 across here. All right, now you can see R1, R2 serial, R3 is parallel to that. Okay, so let's connect now these things. Now this end should be connect here. Okay, these two should be now parallel, should be look like that. Similar connection on the other end. Okay, and now this voltage should be connected parallelly for both of them, which means you have to get the connection from here, start from the voltage supply, and then go up, and then connect somewhere in between. Then that's a parallel connection. Okay, remember parallel means voltage should be the same between both ends. Okay. All right, then that's it. Very simple idea. So let's complete the circuit first. Okay, same other side. Start from here, end of the switch, go up, and then connect that somewhere in between the lines. Okay, not to the top end, not to the bottom end, somewhere in between the line. Then you have a parallel circuit. Okay, parallel mean voltage across should be the same. Okay, good. Any question? And then let's measure current. So the current across this resistor R4 is already, I have a sensor, and then I need to have another sensor, current sensor, to get the current across the other one right here. Let's put another current sensor there. All right, now those two will give us the current. Now, when you measure in the voltage, you can change the voltage, two sensors, because otherwise there are going to be many waves on your oscilloscope, which is not really easy to observe all of them. Let's measure two current sensors and two voltage sensors. Okay, so I had two voltage sensors earlier, so I have one here, voltage 1, and then I will need one more voltage sensor. Let's bring that and then place it somewhere here in between first. All right, so that's it, very simple. So now if you run the circuit, okay, good. Now you can see many curves, right? You see 1, 2, 3, 4 curves, right? Or the waves on your circuit. Good. Following, any question? So the two blue lines, the light one and the dark one, is actually voltage across R1, right? So I need actually voltage across R1, which means the difference between the top one and the bottom one. Top one is actually close to 2 volts, so that is very easy. So now you can see right here, all of these are actually called the input probes. So the input probes will appear like the PR1, PR2, PR3, and then so on, right? So the two of them measure the voltage, other one measures the current. It says V1, V2, other two says the I across R1, I across R2. So that R3, that says the resistor close to that sensor, okay? That's how it reads. Okay, now I need the y-axis voltage, but I need the first probe to be voltage 1. Okay, let's change that and then move that voltage sensor all the way to the very top. And then value should be very close to 2 volt. Okay, should not be larger than 2. Can be slightly smaller than 2, but should not be larger than 2 at all. Okay, very close to 2 volt. Okay, that should be close enough, 1.9897. Then my cursor number 2, it need to be B2, so that you can see the color changes, right? It now becomes a dark blue. So the move that very close to dark blue top edge. Okay, now I need the voltage across those two, difference between them, divide by the current passing through top one, which is actually the pink line, right? Now you can see it's difficult to read that, so which means you can go into that line and then change that. This is now milli 50 to milli 50 positive and negative. Let's change that value slightly because it's difficult to read there. Let's make it small a little bit. So let's do 30 instead of 50. Now you can see that shifted, right? So 30 to 30. So that too much. Maybe I had zoom in probably. Let's try 60 to 60. Positive, negative. Okay, now it's visible, right? All four lines should be clearly visible and then separate out, okay? That's the idea. All the maximum points should be separated out clearly, okay? Good, any question so far? Okay, now that's it. So the calculation is very simple. So you have the voltage values 1.9897 minus 1.4991 divide by current passing through that, which is actually this pink line. So you can read that even by bringing cursor close to that, but the best way to read is actually by using the cursor. Okay, let's do this one first. Now we are working on next circuit, circuit number 2. Circuit number 2, same, only difference is that R1 and then R2 serial, okay, that's the only difference. These two serially connected and then R3 now parallelly connected to that circuit, okay, that's the only difference. Circuit diagram should go here. Circuit diagram, you can save a picture, but you can copy paste later when you rearranging this for your report. Okay, now let's measure. Now I need to find V1. V1 is the voltage across between these two, 1.9897 minus 4991. 1.9897 minus 1.4991. So the volt, and then current passing through that, you have to measure that. So that is actually, you have to change the cursor again. So I need now cursor voltage. Let's change the cursor number 1 into resistor R1. Current passing through the resistor, pink color. So bring the pink color right here. Slowly click and drag to the very top. And then stop there and then read that value just below here, 33.664 milli. So I had 33.664 milli, 33.664 milliamps, okay. Then take the ratio between these two. So that will be the value of R1, which is measured V1 over I. Okay, let's do the calculation. So what we have, parentheses 1.9897 minus 1.4991, close parentheses, divide 33.664 multiplied by 10 to the power minus 3. So I'm getting 14.573. 14.573 ohms. Now that is the calculated value. You have to do percentage different. R1 expected value is 15 ohms. R1 calculated value from your experiment is 14.573 ohms. So that's the percentage difference. Now I have to do this for other two resistors, right? I have to do the same by calculating V2. I gonna be the same across V2. Now, what is the voltage across V2? You can see the other end of the V2 connected to the negative, right? So I don't need to spend really time on doing that calculation. We know V2 should be the value of this dark blue line, right? That's directly 1.4991. So you can save the time that way. V2 gonna be 1.4991 volt, and then current passing through the same, it's the same segment, same current, right? 664 milli. Now you can see how these are connected, because now what we're doing is AC circuit analysis, but you're doing the calculation by using Ohm's law, and also you have to have the idea of Kirchhoff rules, things like that, right? If you have a same line segment, current must be the same. So which means let's calculate R2, which means V2 over I. Let's do that calculation. So what we have 1.44991 divided by 33.664 multiplied by 10 to the power minus 3. I'm getting 44.531. 44.531 ohms. Now you do the percentage difference between 45 and then 44.531, right? So you do the same calculation for V3 and 9. When you do V3, you can see voltage across V3 is the total supplied voltage, right? That also you already measured. You don't need to re-measure that. That should be 1.9897 volt. And current is the value, which is this green line. You change the cursor 1 or 2 into current passing through R3. At a time, you can have only 2 cursors. This is very similar to the real oscilloscope too. Okay, at a time you can have 2 cursors, and then change this. Now you can see cursor number 1 change the color already. Change that into very top of that green line. That green line, green curve represent the current passing through the resistor number 3. So that value below right here, 30.690 milli. Read the units carefully, okay? 30.690 milliamps. Let's do the calculation for resistance. 1.9897 divided by 30.690 times 10 to the power minus 3. I'm getting 64.832. So if you do the ratio, R3 gonna be V3 over I2. Let's say this is I2. I am getting 64.84832. 832 ohms. Now you compare this with the expected value 65. So that's done for the circuit number 2. Okay, following question? Everybody okay with that? Question? No questions? Okay, then let's continue. Next circuit is last circuit. So that is R2 and R3 parallel, and this should be R1 serial, okay? Current, you have to measure the right curve, okay? If you look at it carefully, the color. So this A represent the current, okay? So you can see 2 colors with the letter A, pink color one and the red color one. Those are with the letter A, those are with the current. So if you want to measure certain thing, you go into the cursor, right hand side, says the cursor, and then you change a one cursor into certain color. So if you want the current passing through top segment, that says PR4 IR1. So that is the current one. So you can see color changes automatically to that color, right? So the click and drag all the way to top of that curve, then read that number just below here. It tell you the same color, cursor number 1, pink color, and the value is 33.451. And if I want to have the current other one, I can change the other cursor into current passing through the bottom. Now you can see it changes into green. Now bring that just on top of this green line and then read that number. That is 30.903. You can see the details correctly with the right color, right? So the pink color says the cursor 1, current passing through the top segment, and the other color says the cursor number 2, current passing through the bottom segment. Now you have to get the picture, right? You have to save a screenshot of this circuit diagram separately and another picture with all these curves, right? So that's important, all these waves. So those voltage and current waves are very important because those are the one we're measuring now. Okay, so let's build the other circuit then. Any questions so far? Now all you have to do is, circuit is nothing much changing. Only thing you have to flip is the R1 and R2. Those are the two you have to flip, right? So what I'm gonna do, I'm gonna delete R1 from here, and then you can see it deleted all of these. So maybe I have to delete this circuit too, this part of the segment. Okay. Now let's bring another resistor. This resistor also I have to change. Now R3 should go to the top. R3 and R2 should be now R2 and R3 should be parallelly connected here, serially connected here, and then R1 should be parallel to that. Okay. Please change that there's a small typo here on your table. It should say R2, R3 parallel. First one is R1, R2 serial, R3 parallel. Now this should be R2, R3 serial, R3 parallel. Okay. R2, R3 serial, R2 parallel. Let me write it down that on this table. To clarify circuit number 2, let's do this one. Circuit number 3. Let's do R2 plus R3 serial. And then let's put R1 parallel. Make sense? So there's a typo on your table. Okay, please change that. And then let's build a new circuit then. It's a very same thing. Okay, there's nothing difference at all. And then I have to change this value into now 15 because that is R1. 15 ohms, 45, 65, all good. Then change this position and then build the circuit. Now you know how to build the circuit. Just click on any endpoint and then that circle appear and click and drag until you go into the other end and connect the other end. Okay, and then connect the other connections. R2 and R3 should be now serial, which means should be on one line, and the R1 should be on another line. Okay, that's the only difference. Okay, good. And then let's connect the outside voltage to our circuit, new circuit. All right. Okay, any questions so far? Now, again, the measurements are same. It actually, there's no difference at all. It almost the same measurement we're going to do again by using new circuit. I already have all the sensors are there. You don't need to change the sensors or anything. Just leave it like that. We just need to take the values. Okay, so we need the current sensor on the top and the voltage two sensors, and that's it. Click the icon run. That will give you a new 4 curves, right? You can see. Now you can see this red line is actually too much large now. So I have to change that particular line, right? So to change that, the easy way is that. So click on the voltage Click on the voltage and then select the axis. I want to change the voltage on my axis. So let's take a look. So there's two voltage axes, right? So I need, now it is visible. Okay, so I'm automatically adjusted. Good. Okay, any question? So all four should be visible like this. Okay, all four lines should be separated out, all four curves and then visible. And again, you're going to measure the same thing, right? So we're doing the same calculation. Actually, there's no any new thing. So again, we're doing the voltage across the resistor 1. And then I need the current across resistor 1. Take the ratio, that will give you the resistor 1. So that's going to be V1 over I1. Right, let's find the V1. Now the V1 is actually, you can see resistor 1 is connected to this bottom line. Voltage across that is the output voltage. You don't need to really re-measure that. That is the voltage of PR number 2. So let's measure that. So I need to have the voltage, but I need the value on PR number 2. So cursor, click on that voltage on PR number 2. Voltage across PR number 2, this light blue line, just click and drag. That should be very close to 2 volt, but there's a reading error, so we have 2.0044. Let's read that one, that's okay. That will be our reading error. So now what we have, V1 is 2.0044 volt. Now I need the current passing through that. That is actually this green line, right? So you have to change that current axis. And then the cursor, you have to change the cursor into 1 or 2, doesn't matter which cursor is, but you have to read which one you're selecting. I need the current passing through resistor number 1, okay? So that should appear like the green on your cursor. Then click and drag all the way top of your green line, okay? So that value is appear below here. That is 134.07 milli, okay? When you read the data, read it with the right unit, 134.04 milli, 134.07 milli. So calculate the resistor R1 to see whether I'm getting the right value. What's the voltage? 2.0044 divided by 134.07 times 10 to the minus 3. So I'm getting 14.95. So I expecting 15, right? 14.950 ohms. Now you have to compare this with the resistor 15. So that is the resistor number 1. Then you do the same calculation, voltage across V2, current I2. And then same calculation you done earlier, voltage across V3, current I3. Now you can see, if we do this with the DC circuit, the measurement and everything was very, very easy, right? So we put it, the circuit on our simulator previously when we do experiment number 3, 4, and then all the way to the last few experiments. And it was very easy to measure, but now we are measuring by using the oscilloscope. You have to spend a lot of time really to do that measurement, right? You have to carefully get the measurement. Now, still, I'm not doing really careful measurement because I bring this cursor very close and then just read it without much worrying about the error. But you can't really do it if you're really doing this for some particular application or something, right? So those are the time consuming places there. All right, now I need the voltage, this dark blue one, to get the voltage different, right? So I need the voltage axis cursor. Let's change the cursor number 1 into the dark blue. That is the voltage number 2. Let's read that one. voltage number 2. So that value is about 1.1814. 1.1814. So this is going to be then difference between 2.0044 minus 1.1814. That's the voltage across resistor number 2. Okay. Voltage across resistor number 2, and then current passing through resistor number 2 is the current on the top line. That is this pink line, right? So you have to change the cursor into current passing through resistor number 3, because number 2 and 3 are on the same line, right? So click and drag pink color cursor top of the pink color sinusoidal curve, very top. You have to change very slowly the position. Okay. All right. Now read that number, 19.381. So that number is 19.381 milli. Okay. And then let's calculate that. What we have, the voltage is different between 2.0044 minus 1.1814, close parentheses, divide 19.381 multiplied by 10 to the power minus 3. I'm getting 42.46. So if you do this calculation, R2, V2 over I2, so I'm getting 42.464. Now we expecting 45, right? See that error? It's really large percentage error, because considerably larger, even it is 42 and 45, but in this kind of analysis that is considerably larger, because when we read our values, that top cursor is not on the right location. That's the problem. So you have to redo that as closely as possible to get the right value, right? So the voltage, and then you have to do the percentage difference between them, right? Then voltage passing through resistor 3, you don't need to remeasure, that already there, 1.1814. Current passing through that, you already have 19.381 milli. Then you take the difference between them, 1.1814 divided by 19.381 times 10 to the power minus 3. So that will give you 60.95. So R3 is V3 over I3. I3 is actually same as I2, so that is giving me 60.957. So that, okay, there's a little bit of percentage error, that's fine. That's just our reading error. It's not really anything real. If you spend a little bit more time and then try to read this fairly accuracy, then you will get actually better values. Now, for example, this top of cursor number, this cursor number 2 right here, this pink line is not really visible, right? So we are not really whether it is touching or not. So to see it clearly, what you have to do, little bit zoom in the cursor pink one. So click on that pink line, and then right here, change this minimum and maximum values. So zoom in means you can change this into a different number. So then you can actually zoom this in. You can see now that's getting a little bit larger. So you need actually more higher values, right? See that? So likewise, you can actually change it. Let's change it a lot to see what number I'm getting. Let's try with 50 milli. Okay, that much better. Or you can make it more larger. Make it to 20. Both numbers should be same. Okay, now you can see it much larger. Now let's bring this again, cursor number 2, all the way to top of pink line, okay? And then read that number again and then compare with the previous value, whether we getting the same or not. I want to make sure we have fairly good accuracy on our result, right? So seems to be last one I got large percentage error. Now let's read that number. Cursor number 2, now reading 18.230 milliamps. What's the number which I got earlier? Now see, earlier I got 19.381 milliamps. See the difference, right? Now let's do this calculation with the new value, 18.230. If I do with this 18.280, 1.1814 divide by 18.230 times 10 to the power minus 3. Now my accuracy is much better because I'm getting now 64.8. So use this current, change that current into new 18.230. See the difference, right? That's the idea. So you have to really spend a lot of time when you do this kind of analysis. You can't just read something and then move forward. That's not the way. So now I'm getting good answer for a 64.805. That's better because I expecting 65. So that's a good answer. Let's try the previous one too with the new current 18.230. So let's check that one too. 2.004 minus 1.1814 close brackets parentheses division. Now 18.230 times 10 to the power minus 3. I'm getting 45.14. It's a very good accuracy now. So I'm getting this, sorry, not that one. This one, second one, R2. So now I am getting 45.145. So now the expected value is 45. So we are really within the margin of error now. Okay, so that's the idea. Any questions so far? Now, these measurement, these circuits, you have to do very carefully and then very smoothly. Otherwise, you will get a large percentage error. All the decimal values, person to person, must be different. Okay, there's no reason to have the same numbers at all, because we're reading to 5 significant figures. Collection of those numbers must be different. Okay, and you have to get the pictures and then so on. Okay, so the very last part, which we actually call the Lissajous figures. What's the idea of Lissajous figures? Let's take a look. Anybody have any questions so far? No problem. Okay, so let's take a look. What's the idea of Lissajous figures? We completed every single data point on all the tables. Okay, so only thing I did not do is the percentage different. So that should not be difficult at all. So let's see. Lissajous figures happen because of simple reason. If you apply two waves, so the one wave oscillate on x-axis and then the time axis. Let's say one wave oscillate on y-axis and then let's put the time axis into x. And then we put another wave, will oscillate on z-axis, let's put the time axis same. And then if you let those two waves to combine together as a single wave by putting the time axis same, because you know now the both waves has the same time axis, right? So what we're doing is actually this. So let's put one wave which oscillating on here, y-axis, and then this is the time axis, x, right? So this is oscillating on y-axis. Now this is the voltage on volt, but this is y-axis. Now let's put the other wave Let's put this oscillating on z-axis. You know the third axis here, that is z. This is t. Now this guy is oscillating look like this. So it goes on here. So that do the oscillation this way. Now this oscillating on z-axis. Okay, now this is wave number 2. This is wave number 1. Wave number 1, wave number 2. Both time axis is same. Okay, time axis is same axis. Now we put the same time axis. We combine these two together. If you combine by keeping the time axis together, you will get a new wave. So that wave actually called the Lissajous figure. So the only problem with the online simulator, we can't really see the Lissajous figure. There's no way to combine those two in our online simulator. Because of that, you can see on your lab manual, I put the link to the YouTube video. So that's a very good demonstration. It's not a lab or anything. There's nothing to actually do much there. If you click that link, then you will get a YouTube video. Okay, now if what you have to do actually, you have to observe this YouTube video and then observe at least 3 different Lissajous pattern. Okay, you can see table number 3. It says 1, 2, 3. So which means you have to observe at least 3 different Lissajous pattern and then either take the picture. You can take the screenshot from that video directly, put it here, and then tell the information. What is the frequency on channel number 1 he's applying? What is the frequency of channel number 2 he's applying? What's the pattern he observing? So that's just the observation, and then put the information here. I let you to try that later when you're doing the report. Okay, any question, concern? Everybody okay? No problem? So let me scan through this one a little bit to see at least one nice Lissajous figure on his diagram. See, there is what's going to happen. So that is one of them, right? So you scan, this is a simple short video. See, that is another one. He's actually telling you what are the frequencies he's setting and then so on. You have to observe accordingly, okay? See what's going to happen if you have two waves and then you keep the x-axis constant and then you combine those two waves together, you will be getting actually some sort of three-dimensional figure. See, that is another one. So if you're doing this in class, we actually can do this and observe. You can see he's using analog oscilloscope too. Now this is the analog oscilloscope. You can see all the variable, all the knobs and everything. He's give you a little bit of information too. If you're more interested on learning analog type oscilloscope, all the basic operation, this guy has a series of videos actually for oscilloscope, things like that. It's some very useful videos, okay? And you can see that is another type of Lissajous pattern. Good, any question? I will let you to check that later. There's nothing much else to do there together. So it's just the observation, okay? All right, guys, any question? No problem. Okay, so let's continue to our previous chapter and then discuss a little bit of information there. We have about 20 minutes. Anybody have any question on the lab? Now, both of these lab report are short lab report, okay? Lab number 7 and lab number 8, both short lab report. Lab number 9 is also short lab report. Lab number 10, I mentioned earlier, there's no report at all. You just need to upload only the table, calculation and everything, okay? Yes, yes. No, the data sheet doesn't matter. Don't worry about that actually. The in-class data sheet, you can upload without that. Table tree, no need to be there, but you need that for the report, okay? Good. Okay, any question? Now you can see even by using the simulator how much time we have to spend to complete this kind of lab, right? So if you're doing this in class, you have to really build the circuit and then measure everything. So that's where the time consumes. So if you're doing this in class, it's taking a lot of time to build the circuit, and then simple mistake, like if you have a loose connection or something, you're not going to see the observation we would like to see. Then you have to recheck all the circuit and everything. So it's a lot of time consuming this kind of work. Okay. All right. So let's continue. Anybody need any help or any question so far?